Hello and welcome to Unprofessional Engineering. My name is James.
You got Luke.
Luke, today we're tackling a topic near and dear to my heart, finite element analysis.
Oh, you said
Is that,
FEA.
what did you go for?
I joked with this earlier this week, and actually FEA does mean something else. It's an aging term, and
Uh-oh.
it's feeling every ache. And I did all of my research on geriatrics.
Well, I can understand with your advanced age why you would go that direction.
Yeah. Speaking of geriatrics, man, does my back hurt today? Whew.
Does it?
Yeah.
You're
It was
old.
a very uncomfortable evening. My air conditioning went out yesterday, and lots of tossing and turning. I didn't sleep well, so my back is a little sore. So if I'm a little salty today, folks, that's the reason why.
Blame it on the heat wave.
Yes.
All right, so finite element analysis. Luke, do you know what it is?
That's the stuff that I ask other people to do.
That's true.
Whenever I want to know if something's going to break.
So here's what Wikipedia tells me it is. How about that?
You're an engineer and you're going to you're going to use...
No, I'll give you my answer
commentary.
After this.
Gotcha.
Yes. So FEA or FEM, which would be Finite Element Method, is the most widely used method for solving problems of engineering and mathematical modeling. Typical problem areas include the traditional fields of structural analysis and heat transfer. And the FEM method is a numerical method for solving partial differential equations in 2 or 3 space variables. So that hurts my head.
You can't even say PDE without a little verb. You're like,
I know. Differential equations always sets me off. So a little background, I was involved with FEA for probably 10, 12 years of my career. So when I started out of college, I worked for a finite element analysis company named Algor, which was then acquired by Autodesk down the road. So a whole bunch of experience with FEA. So I love the topic. And I would always describe it to people as, because no one ever knew, I would always describe it as, we take an object and we break it up into little bitty parts, and we understand then how it's going to react if we put a load on it. And then they look at me funny and I say, imagine the chair that you're sitting in. And they're like, okay, now what if it wasn't designed to hold your weight? That would be bad, it would break. That's what we're doing, but for everything. It could be a chair that we're analyzing. It could be a desk. It could be 2 cars colliding, and you could see the cars smash into each other and then better understand what parts of the car's going to crumple. So it's pretty simple when you think of it that way, at least to understand what the software is doing. It's doing calculations to determine how these parts are going to fail. So pretty easy.
And I think it's the key piece is what you mentioned was breaking it down, and we'll talk about mesh a little bit later. But the idea is, so if you're doing a simple beam calculation, you probably could do this by hand if you wanted. You
for sure can.
Yeah, it's relatively easy if you know the equations, and so. But the problem is the minute you get into complex geometry, so it's not something that's square or circle. There's lots of perhaps detail to it. The other thing too that you need to think about is you get into multiple materials. So maybe this thing just isn't exclusively steel or wood. So you need to understand how a system is going to behave, not just an individual metal part. So if you look at FEA, you could use that to calculate, a beam bending or deflecting or breaking. But the reality is you're going to use this whenever you have these more sophisticated systems with multiple materials and conditions. And then there's different types of analysis that you do with FEA. Like you could do, a static analysis, or you could do a transient analysis. You can do linear and nonlinear. You have all these different, analysis types that vary in complexity that we may or may not talk about. We'll see.
I think we should. Oh, maybe not just yet. I would like to talk a little bit about the history of FEA before we get into how it works, though. What do you say?
Of course we can. So, in all of my crack research, James,
a lot of research
and I am a crack researcher. And there's no one specific person that like coined like FEA that I could tell. But if you take this all the way back, the two cats that invented this, they were, and I can't find my notes as soon as I said that. So this goes back to
I saw the 1940s. Now, these might not be the two people that
oh
you're
no,
talking
I'm
about.
talking about Isaac Newton. Like
Oh,
so basically
he
FEA.
did not work with FEA,
Well,
at
he
least not
didn't.
from a computer
But
perspective.
fundamentally, he developed the the differential equation. So after calculus was invented, I forget what year that was or whenever that was developed.
Check out our episode on Newton.
Exactly. So Isaac Newton, and who was an English physicist, and then a German mathematician named Gottfried Leibniz.
Sure, I
I
think you
think is
nailed
how you
that.
say his name. So they independently invented the differential equations and calculations that are the roots of what FEA is,
Uh-huh.
the equations necessary to solve. And then what I think you're going to talk about history-wise, and I have some information too, is they took these equations that you would typically do on paper, and they basically put them into a flux capacitor computer,
Uh-huh.
and
Uh-huh.
then all of a sudden you have instant answers rather than answers in days or weeks or however long it would take to do so.
Yeah, so Alexander Pavlovich Henrikov.
Nailed it.
He's a Russian Canadian structural engineer and the founder of the Finite Element Method, as well as Richard Courant, who was a German American mathematician. Not a mathematician, a mathemagician, because this stuff is way past
Oh
your basic
yeah,
math. How about that?
for
But
sure.
they were back in the 1940s, and this was early on FEA. So probably didn't really resemble anything that we would look at today, right?
No.
So then I think the most interesting part, and I don't want to steal this from you because I know you like talking about it, I believe, would be the space program.
Oh, here we go. Early
Here we
1960s.
go.
Ready?
Okay.
In the early 1960s, a small analog computer manufacturer for aerospace industry was awarded a contract from NASA. So remember, we're shooting people to the moon and doing all this crazy space stuff with NASA. In the 60s, they needed a way to understand, how, what they were building was behaving. So they were contracted to develop what was called a general purpose finite element analysis code. This company, and I never knew the name of this company, like I know the
Uh-huh.
acronym, but the name of the company was McNeil Schwindler Corporation, or MSC. Those cats are still around. And then they actually kept on creating a commercial version of the FEA code that they developed that is now known as NASTRAN. And you can actually, I went on the NASA's website. You can download like a 1995 version of the original NASTRAN code, which
Yeah.
is crazy because it's an open source code that you would then plug into different solvers to do different things. So that happens back in the 60s. But a fun fact,
Ooh.
the name used for the program originally in the 60s was GP SA, and it was an acronym for General Purpose Structural Analysis.
Oh, that's good.
Eventually, the formal name approved by NASA for the program was NASTRAN, and that acronym stood for NASA Structural Analysis, with the STR in structure and AN in analysis. So that's where NASTRAN came from. I
Cool.
never knew that.
I don't know if you've been to the Carnegie Science Center in a long time. I
It's
know
been a while.
probably not, since the kids getting older and whatnot, but they have a little exhibit there about space, and NASTRAN is mentioned in there, and how NASA kind of developed NASTRAN and how it got them to the moon. So super cool stuff. Was really exciting to me.
Second fun fact.
Yeah, I need to hear another
So
fun
the
fact.
original software architects that developed NASTRAN, the first one is Joe Mule. Sorry about the
Yeah,
last name, Joe.
Joe
He was from
Mule,
NASA. Gerald Sandler, he was a
Sandy.
NASA employee. And then Stephen Burns, or Stephen Burns, depending on where you're from. And he was University of Rochester. So those are kind of the three original software developers for
The big
NASTRAN.
wigs. All right. So before we get on with any more of this, I think it only makes sense that we take a break for a word from our sponsor.
I have to assume it's NASA or the Carnegie Science Center.
We've said NASA about 472 times, but in fact, they did not sponsor us because they're jerks. But we do have a couple of shout outs. Shout out number 1 is Mosley M. Suggested we do an episode on the rotary engine, kind of like the 90s Acura NSX, which I will have to take Mosley's word for it because I don't know anything about that.
My brother drove a Mazda RX-7, I think, that had the rotary engine.
Interesting.
And yeah, it was a very problematic car.
Oh, was it?
Problematic engine. Yeah, the rotary engine was not a good. Obviously, it doesn't really exist anymore. So we could do that. That's interesting one. I like that one.
Okay, we'll add it to the list. I think it's already on there actually. And our second shout out, and I apologize for just destroying your name.
Oh, you'll nail it. Don't worry.
Andisha.
You nailed it.
Well, anyways, this is our number 1 fan from Iran.
Nice.
Right? Pretty cool, huh?
We are so international.
Starting the day out with Unprofessional Engineering and a cup of coffee in Iran. So super cool to get that email and see how far we've come.
We got a place to crash if we ever go to Iran.
I probably will be there once the pandemic's over.
Our number 1 fan better have a place for us to stay.
Yeah.
Sweet.
Put us up for the night. That's right.
Nice.
So that was super cool to hear as well. If any of you would like an amazing shout out, because all of our shout outs are amazing. If you just want to say hello, if you want some topics to give us to research, if you want some amazing stickers, why don't you email us at unprofessionalengineering@gmail.com.
Make sure you subscribe, make sure you like, make sure you give us some reviews. And as always, yell at your Alexa device and you can hear the latest episode of Unprofessional Engineering right in your ear holes.
Ear holes. Now, before I start really just geeking out on all of
You're such a nerd.
The bits of FEA, I thought talking about some of the companies that exist out there or products that exist out there that do FEA would make some sense.
I think it'd be good.
So I think probably the biggest, right, would be ANSYS.
That's the one everybody knows, I think.
Yeah, that's the one everybody knows. It's used by everyone. Man. They're in lovely Cannonsburg, Pennsylvania, which is
right
just
down the street.
Yeah, like literally almost a neighbor of Luke, right?
Practically.
So that's really cool. So when we get fired from Autodesk, maybe we'll be able to work there. But speaking of Autodesk, they actually have some finite element analysis software as well. So they purchased Algor, where I came from. I was probably the best part of the deal.
For sure.
And then they also have some FEA in their Fusion 360 product and their Autodesk Inventor product.
And in 2014, they purchased NEI NASTRAN, and that's where Inventor NASTRAN is. We had some really sweet built-in analysis tools. So, and you know me, I'm a huge Inventor user, so I love being able to do simulation.
That's right. So ANSYS, I always consider the big kid on the block. Another really big one is Abacus, which I believe has been purchased by Dassault, along with many, many, many other things. ComSol is another one.
MSC.
MSC, yep. Cosmos Works is part of SolidWorks, or at least it used to be. I think it's still around. LS Dyna, I'm going to call out as its own thing, but ANSYS finally purchased it. They had a big time integration back in the day with LS Dyna and ANSYS Classic, which was just a miserable product to work with. But the amount, like the types of calculations you could do with LS Dyna were out of this world. I used to do analyses on shipping containers that were shipping nuclear fuel, like nuclear waste around. Wow. And so I would have to have all of these baskets, which were like 40 parts with the fuel, which was another 10, sitting on top of another basket. So we're talking 90 parts inside of this giant shell. And I'd have to do a drop test where this thing would drop 20 feet onto, we would call it like an infinitely hard surface. So imagine dropping onto concrete, and you would have to be able to see all of the parts jostling around and banging into each other to understand the stress. And this thing, it was on a beast of a machine, don't get me wrong, but they'd be able to do this overnight or over 2 nights. And
I feel
that blows my mind.
Running an analysis that has nuclear ramifications should have found a far more qualified person to
I
do it.
know.
I'm just
It's
putting that
really
out there, James.
scary.
I don't mean to be a jerk,
No,
but
it's very scary. I agree. Fortunately for everyone, I no longer am involved with that, so that's good. So NASTRAN you mentioned. SimScale is another big one out there right
yep.
now. It's 100% web-based, and then there's a ton of other ones, but those are a lot of the big
There's
players
a
out
lot
in
of
the game.
specialty ones out there that kind of choose, like most of the ones we mentioned are they have general purpose applications, but I know that there's a lot of specialty ones out there that actually pick very specific applications that they want to solve. So that's kind
Yeah,
of an interesting angle to take, is to pick one thing that you're really good at and work it. So
that's what we do. One thing we're really good at, which
yep.
is not knowing much about stuff.
Mm-hmm.
Okay, so before I get into more nerdingness, is there anything else you wanted to cover?
Not
Eh.
not really. I have a little bit of stuff on, some of the things that go into FEA, and I have a little bit on the difference between FEA and CFD, because you know me, a CFD, an
Yeah.
ex-CFDer. I had to bring that up a little bit, but yeah, we can continue on with yours.
Okay. So types of analyses. You've touched on this a little bit, but there's a whole bunch of them out there for FEA. So linear stress would probably be your most basic analysis type. So this would kind of be like if you sit on something, are you going to understand if it breaks or not? All of your materials are in the linear range, meaning, they're not like in the plastic range. So think of like a steel
Yep.
versus like a rubber material. Nonlinear analyses would be when you're working with something like rubber or something of that sort, or something that goes past the yield point. So say something fails, but it's not like catastrophic where it breaks in half. Once it goes past that yield point, the material properties change. And so you
Mm-hmm.
have to take that into account. And fortunately, we have computers now that can do that for
Yeah.
us, because doing it by hand is terrible. You have thermal analyses, which generally speaking, you'll be able to have like a heat source, let's say, and then you'll be able to determine how that heat radiates out. So electronic components are a big thing for this, where you have all, and if you haven't checked out our episodes on like microchips and what was it, the was it CPUs that we
Yeah,
did,
I think so.
and transistors, that was the other one. Check that one out, but it talks about how they get hot and things like that. You're going to be analyzing that sort of stuff with a thermal analysis.
Yeah.
Or if you're bringing a spaceship back from space, you're going to be analyzing how hot the exterior of your shuttle gets, to make sure that the parts aren't going to fail because of that.
My guess is
Oftentimes
we'd be making some marshmallows.
I think so. You'll take those thermal results, though, and oftentimes you take that thermal distribution on your part and then put that into a linear analysis or a nonlinear analysis, and then you can see the resulting stresses from the temperatures.
Wait, because stuff behaves differently at different temperatures.
Sure. Yeah.
You know.
So you can see like how it changes over time with the changes in temperatures, as well as the changes in loads that you have applied. So pretty cool stuff. Electrostatics and electromagnetism. I was always terrible at this. I have a friend who runs a switch company, like big engineering switches,
Mm-hmm.
and they use ANSYS to do this. Really interesting stuff. But just think of how magnetism works and running electricity through stuff. And then there's a whole bunch of other things that fall under natural frequency calculations. So this would be like response spectrum, frequency analysis, critical buckling. So buckling would be like think about the pop can trick, how you can stand on a pop can and it doesn't do anything, but if you ping the side of it and it'll just crumple, it'll be doing calculations like that. Or natural frequencies would be if what's that bridge, the Tacoma Narrows Bridge, that got all wavy and terrible failure? That's because they didn't look at the natural frequencies caused by the wind that was passing by, I believe. And so now we have computers that can look into those calculations for us. And then the last one I'll mention, I always thought was pretty interesting, was like a fatigue analysis. So not everything breaks because it gets hit too hard or because it has too much weight put on it.
But if it
But
gets hit
often,
multiple times,
right, exactly. If it gets hit multiple times, if it gets bent back and forth, bend a paper clip back and forth a whole bunch of times, like at the start, it's a little bit tough to bend, but then it gets real easy. And then all of a sudden it's brittle and snaps. That's because of the number of cycles that it can go through bending back and forth. So the it fails due to fatigue.
and it's
And
also fun to take that really hot part of the paper clip that got really hot and you press it on the kid sitting next to you, seat's hand, and then
you
you
were
get
a
the tension.
bully in school, weren't you,
Oh
Luke?
my! I did that so many. You do it and it gets really hot, and then I got the tension probably at least in elementary school, probably at least 3 or 4 times for that.
Hold on, you got detention in elementary school?
Oh, I was a bad kid, James.
Oh my goodness. We need to
I was
discuss
bad.
this later.
Yeah.
All right. Before we go on with more of my nerding, I think, goodness, we should take a break for this week's Luke's Rant.
Okay, so my rant is going to lead us into our next topic, and this is mesh is the worst.
Oh my goodness.
So if anybody out there has ever done any analysis, you know that you have to build a mesh. And I don't know about you, James, but like the most complicated part, like as an engineer, like I know the condition, I know the material, I know where it's being held, I know, like, all that, but then you got to deal with this mesh and make this thing solve. And mesh has just been so I mentioned I used to do CFD. So I used to work for Blue Ridge Numerics, who was also acquired by Autodesk. And we were...
And CFD is like the next door neighbor to FEA, right?
Exactly. Actually, you can do some, like you can mix and match the code. Yeah. So like you mentioned heat transfer. You can do that with FEA, or you could do that with a CFD, Navier-Stokes style equation to do the solving. But meshing has just always been, and I think most analysis tools, it's kind of the Achilles heel of most analysis tools because, number one, you have to have super clean geometry, slivers and gaps and overlaps and spacing and all the different things that like engineers design into their systems to make them hyper accurate is just a bear for most meshing tools to solve. And there's this, I remember back in the day when I was at Blue Ridge, there was this meshless solving where you don't need a mesh to do it. And as far as I know, that has never really come to fruition. And everything,
I've never seen it.
Everything under the hood has some kind of mesh. So my rant is whoever builds these meshers just needs to just make it automatic. Like we had auto mesh, but it was never really auto mesh back in the day. So.
It was auto mesh and then troubleshoot as much like for 3 days until it meshes. Yeah.
Delete part, get rid of fillets, get rid of chamfers.
Yeah. I was talking earlier about that giant part that I dropped, with LS Dyna, blah, blah, blah. The reason it really could run successfully, which I kind of left off, was because my mesh was hand built. Yeah. So every element, so when you mesh something, and we'll get into this, you make it like little squares, we'll say. And so everything that I built was meshed perfectly. So it was all these nice little squares everywhere. And then you extrude them down into beautiful little cubes, which is much easier to calculate your answers for because you don't have any of these tiny weird shaped elements. Yeah. So that was kind of the secret sauce behind getting that to run. But yeah, man, meshing, just the worst. All right. Do you want to talk about that?
Yes, let's talk about meshing a little bit. So, so modern FEA tools, like we've been talking, NASTRAN was, the beginning of this. There's this underlying mesh that happens, and James he just mentioned it. So there's different types of mesh. Like there's, mesh that's, squares. There's mesh. There's 2D mesh. There's 3D mesh. There's tetrahedral stuff. There's triangles, hexes. Yeah. There's all voxel mesh. I mean, there's so many different mesh types. It's literally kind of crazy, and each one kind of performs better depending on what you're solving. So the mesh might change depending on what you're doing, but essentially what you're doing, and James described this really well at the beginning was, and I normally don't give you any compliments.
Thanks, man. No, I was just taking that one in. Yeah.
So you got this super complicated, nuclear fuel storage system that has all these, parts and pieces that are all touching, and there's no way to hand calculate that. But if I go down to like a millimeter or whatever you choose your mesh size to be, and I say, I want to understand what happens in this 1 millimeter, cubic area, and then the one beside it and the one beside it. So what you're doing is you're solving those partial differential equations, and all those equations are happening simultaneously at each one of those connection points from one piece of mesh to another piece of mesh. And then that's what builds, your final solution and your final results. Like, you could never do that by hand. You could, but it would take you forever and have to super simplify it. So that's what mesh does. It takes these really complicated pieces of geometry, breaks it down into really small, manageable answers. And this is why computing power is such a big deal. I did this one analysis. It was a bus, and we wanted to understand the airflow in a bus. And I simplified the whole model of the bus, and the mesh was too big. And then I cut the bus in half, because you can always mirror results, right? There's all these tips and techniques you can do. You cut it in half, and it's still, the mesh was like, 25 million elements. And it's like, okay, my computer, and then I cut it in a quarter, and then I started cutting it this way. And you basically have all these tricks to manage the mesh. And what happens is computing power gets better and better, you can now solve these bigger mesh analysis. So, and hand building mesh is probably the most time consuming way, but you're pretty much guaranteed that you're going to get good results.
Yeah. Yep. No, that was beautiful, Luke. Well done.
Thank you.
You also touched on the element types. So you have like those 2D elements, 3D elements, hexes, and tets. And tets are bad. You use them because they're easy to get, especially when you're auto meshing something.
Curvature stuff, it does really well with curvature.
But if you're doing like a normal nonlinear or linear stress analysis, your hex elements are usually the best ones to be working with. So all sorts of stuff there. But there's even more that goes into it, like something that you call your material model.
Mm-hmm.
So we talked about this a little bit in the difference between linear and nonlinear, but there's a bunch of different material models out there that you will use. So like we were saying, steel acts a little bit differently than aluminum, which acts a little bit differently than rubber, which acts differently than a tree. So if you're making something out of wood, you have to use like a composite, which has a different material model than steel, which is very basic, because wood has different layers basically, or lamina almost, how it's going to work. But then if you get into something like a rubber or a slimy kind of material, think about a gasket. A gasket squishes very easily, but it doesn't really rupture easily. So you need to use like a hyperelastic material model for that, which has like all of these data points put in there for the way your specific rubber works. And that's the worst part about this, is that you can have a quote rubber material model and you can use that, but those answers are going to be virtually useless for you. It's going to be garbage, because your material properties have to match exactly with what you're using. Otherwise, you get garbage results.
Yeah, and material properties are kind of interesting, because you kind of have to put the cart before the horse a little bit to really understand, because there's all these labs out there. And what these labs do is they take different pieces of material, whether it's rubber or steel, and what they do is they run simulations on these different materials to understand where those materials are going to break, what the stress is, what the strain is. So whatever that material is, you have to know how that is actually going to perform ahead of time, so that you can then input that in your analysis. So it's a little bit where you have to know those materials really, really well. And like when you look at aluminum, for example, you have 6061, and you have and you have just regular, and you have cast iron and ductile iron, and you have all. So even within aluminum, steel, wood,
and those are the basic things.
And those are basic. I mean, now you do an analysis where you have a steel beam with a rubber gasket and a wood spacer with a steel beam on top of it. Now you're dealing with multiple material models inside of one analysis. And you can see how this can quickly, turn into a really difficult thing to do. So nailing down those materials is super, super difficult and time consuming, to be honest. So.
Yeah. So I know we're almost out of time here. There were just a few things that I wanted to touch on, and that would be like some common problems and maybe some tips for your FEA. So common problems, one would be a hotspot. Now, this all comes back to the mesh that Luke was talking about. When you load something up in FEA, you usually use like a pressure on a surface, or you can use a point load, which will
Mm-hmm.
be on one node. So when you mesh something, all of the little squares that you make, every place that the lines come together, that's a node.
Mm-hmm.
So you might put an arrow there and say, okay, I have 500 pounds of force right there. And so the program is going to do a great job of showing the results everywhere on the model except where that load is placed, because it just doesn't have the intelligence to understand that all 500 pounds aren't really being applied right there.
Yeah.
It's kind of like it's happening there, but it doesn't distribute it properly. So of course that's going to show up as a red spot on your screen, and red is bad and all of these things. So to avoid hot spots, you usually do something which would be refining the mesh in that location. Yep. And so if you use a refinement point, that can help with it. It's not going to get rid of the problem, but if you're talking to people who understand FBA and the results, they're going to generally accept that that's not really a big area of concern. Another thing that you have to watch out for is unstable models, and this is usually something that has motion involved in it.
Yeah.
There's 6 degrees of freedom for all of your models, so your rotation and translation degrees of freedom, and oftentimes you don't have enough of those fixed, so that there's just too many calculations for the computer to do, and there's too many options for your part to move around.
You're not
So often,
constraining it.
right. So oftentimes you add these
Completely.
constraints to kind of limit the movement that you know it's not going to take in reality, to kind of help the computer out to get a solution.
Yep.
And then 2 tips would be symmetry. They're kind of the same tips. Symmetry and simplification.
Yeah.
Get rid of any of those details. People that use raised lettering on their parts, because CAD guys love making that stuff because it looks cool.
Raised lettering.
Get rid of it. If you're using etching, get rid of it. Fillets, get rid of them if you can. If they're not going to impact the way the part or parts work, get rid of it.
Mm-hmm.
And even if you have extra parts that aren't really crucial to the analysis, get rid of those as well. Yeah. The less you have, the faster it's going to run, and probably the more accurate results it's going to give you. Yeah, and that leads me in. Oh, go ahead, Luke.
I was saying, I had a tip too. So here's mine. And you could either do one analysis that has everything and it takes 3 days to run.
Yeah.
And, you know, and that happens. I've had analysis take more than 3 days to run. I'm sure you have too. And the challenge is you could make the perfect model and get it to mesh and get it to run. It's going to take forever to give you an answer. And what you could have done in probably a couple of hours is follow all those tips and techniques you've done, simplify, you know, run those really, I hate to say dirty, but run those, you know, really loose mesh, you know, make sure all the fillets and chamfers and all that stuff are gone. And then what you do is you get these kind of answers that are directionary. Like, okay, you're doing the right thing. Let's refine this a little bit better. But why run an analysis that takes 3 days to find out it's going to fail when you can run an analysis in 2 hours and find out it's going to fail?
Yep.
So run those simple analysis first, get the directional feedback, and then start to refine that later on.
Okay. 2 quick stories for you, Luke.
Shoot.
From my FEA days. At my company, I went out and learned how to train people on FEA. And so I went out on my first solo mission in Anaheim.
Nailed it, I'm sure.
I think I did. I was pretty good at training, I think. Anaheim, California.
Yeah.
The first 3 days were linear stress, stuff like that, super basic, right? So that was easy. Then the first day of the complex stuff, I'll say, I'm halfway through the day, and this guy, we'll call him Jim M, which is his name. He worked at Rocketdyne. So this was like a serious dude. He's like, hey, James. I'm like, yeah, Jim. He's like, how old are you? I must have been 22 at the time. I'm like, 22, Jim. And he's like, I think I've been using your software longer than you've been alive. Oh, do you want to teach it then, Jim? And he's like, oh, no, you're doing a great job. Thanks. Keep going.
That's nice kudo.
It was really nice. I ended up going out to dinner with him. Super nice guy.
That's cool. And
then my next story, this was before I was an official trainer. I was in lovely Ann Arbor, Michigan. It was around that area. It was another tiny little town. And we went out with the one engineer at GM that was using our software.
Okay.
And he wasn't in our training class. He just came by because he called a lot because he worked on complex stuff. And he took us out to Ann Arbor for dinner and drinks. And I was a much younger man, Luke. I was 22. I made bad decisions.
I'm sure you made bad decisions.
We'll skip ahead. We rolled back to the hotel at about 3:30 in the morning. And we were like, man, we got a train at 8 o'clock. So I have less than 5 hours to go until I have to be training the next day. And this guy busts out his laptop and he's like, so could you look at my model real quick?
This is 3 a.m. in the morning?
3 a.m. in the parking lot of the hotel, where he's looking at, how do I get this rubber gasket smashed into place, because this is necessary for our engine. And we spent the next hour troubleshooting this guy's model until 4 in the morning. No, we ended up having him send it to us, and we did it offline. But those were two of my favorite FEA stories back.
That's a good one. I like that.
Yeah. So hopefully everyone here enjoyed learning about finite element analysis, or the finite element method, which can also be done by hand, which you will likely do in school if you take mechanical engineering courses.
Be doing some differential equations, that's for sure.
That's right. If you'd like to learn more about FEA, if you just want to say, man, you guys are way smarter than I thought you were, or say we got everything wrong, email us at unprofessionalengineering@gmail.com. And until next time,
see ya.